now that we've seen what it means for a linear transformation to be injective and surjective, what we want to do is we want to look at what happens when they're both injective and surjective. And these are called isomorphisms. So let's start with the definition here. Let's suppose we have V is a subspace of Rn and W is a subspace of Rm. So these are subspaces. Then if we have a linear transformation T from V to W, and T is injective or one-to-one and surjective or onto, then T is an isomorphism. Okay, so this is what we mean when we have a map that's injective and surjective, we call it an isomorphism. And also in this case, we say that the subspaces V and W are isomorphic. So if there exists an isomorphism between two subspaces, we say that it's isomorphic. What do we mean more explicitly here? So let's say maybe more explicitly, T is an isomorphism if we have the following criteria are held. We have that T of X equals T of Y implies that X equals Y, right? This was our injectivity criteria. This was what the linear transformation had to necessarily imply, that T of X equals T of Y implies X equals Y, right? This was the injective or one-to-one property. And we also have to have that for every, let's say W, element W contained in the subspace W, there exists an element V in the subspace V such that when you map V under T, you get W, right? This was the onto criteria. So if both of these criteria are held, then we have an isomorphism. So what does this mean? Maybe more geometrically, right? Well, let's draw a schematic here. Let's say we have Rn, and we're mapping Rn to Rm via some isomorphism T. So let's let this be an isomorphism. Within these Euclidean spaces, we have subspaces. Say here we have subspace V, and here we have the subspace W, right? And so here T is a map of V to W, right? This map may or may not extend to the entirety of Rn and or Rm here. But what an isomorphism does is it's a map that's one-to-one and onto, right? What does onto mean? Onto means that every point in the codomain, right, or in the image is hit. So let's just say we have 4 points here that we're looking at. Onto means that every point in W is mapped to by some element from V, right? And one-to-one means every element in V maps to only one element in W. And so what an isomorphism is it's basically a copy. Like intuitively, you would just think about W as being a copy of V inside a different dimensional space. So everything is mapped one-to-one, but everything in the codomain is mapped to, right? And so this is exactly what it means to be an isomorphism. We don't have anything where, well, if we had one element mapping to like say if we had one element mapping to two elements in the image, that's not well defined even, so it wouldn't even be a transformation. But we don't have, you know, anything that's happens like in a surjection here where you have, say, two elements in the domain V1, V2 mapped to the same W. You don't get that for an isomorphism, right? Basically every element is mapped to some element uniquely, right? And every element is mapped to. So this is what it means to be an isomorphism. Or this is what it means for V and W to be isomorphic. And the notation here sometimes for V and W isomorphic, sometimes you'll see V is isomorphic to W. And if it's explicit, like with respect to a given isomorphism, you may see like this, this equivalence squiggle here with a subscript T, and that's telling you how V and W are isomorphic in that case, right? Usually it's understood in context what isomorphism we're looking at, so I'll probably just drop the subscript. Okay, let's see an example of, well, one, what's an example of an isomorphic map, and how do we show that it's an isomorphism? So let's prove that T of xy equals x plus y, x minus y is an isomorphism of R2 to itself. Sometimes you'll see this as, right, well, this would be T as a map from R2 to R2, or you may see T as a map from R2 to itself. Sometimes we see this notation as well. So how could we show this? When you're trying to prove that something is an isomorphism, you always have to show the following three things. So here's kind of a to prove T is an isomorphism. And this is always true, right? Anytime you want to show that a map is isomorphic, an isomorphism, you need to go through these three checks. One, that it's T is a linear transformation. Two, that it's one-to-one. And three, that it's onto, right? You have to show all three of these things, or all three of these criteria have to be met in order for T to be an isomorphism. So let's do that. Let's first, right? So let's prove this here. The first thing we need to show is that T is a linear transformation. What does it mean that T is a linear transformation? It means we want to show that for all vectors V1 and V2 in R2, right? Because that's our domain here. Our domain is R2. We want to show that T, well, and for all scalars A and B and R, we want to show that T of A V1 plus B V2 is equal to A T V1 plus B T V2, right? We needed to show this linearity criteria, this linearity property. So this is what we want to show. How can we show that? Well, let's take two vectors. Let's say V1 is x1, y1, and V2 is x2, y2. Now let's consider T of A, x1, y1, plus B of x2, y2, right? And so we want to take T of this linear combination and verify that we indeed get this linearity property here. So how do we show this? Well, to show this, we first simplify the expression inside of the function here, or the map. So This is T of, and you can see by two steps, first scaling x1, y1, and x2, y2 by a and b respectively, and then vector addition, we'll get that this is T of ax1 plus bx2, and then ay1 plus by2, right? So what is this? Well, we have to look at the definition of our transformation here, and it's defined as the first component is x plus y. So that's going to be, if we think of this whole thing as x, and then the second component as y, then the transformation is going to be x plus y. So this is a x1 plus b x2, and then plus y, which is a y1 plus by2, and then the second component is x minus y, right? So we have a x1 plus b x2 minus a y1 plus b y2. Now we can simplify this or complicate this, maybe, if that's how you view it, by combining everything that has an a factor in it and everything that has a b factor in it. So if we do that, we'll have a x1 plus y1 plus b times x2 plus y2. And then for the second component, looks like we'll have a x1 minus y1 plus b x2 minus y2. And then we can see if we split this up into two vectors, and then we pull out the constant a for the first vector and the constant b for the second vector, we're going to get a times x1 plus y1, x1 minus y1, plus b x2 plus y2, x2 minus y2. And this is exactly, here, I'll just write it down here. This is going to be a t of v1 plus b t of v2. And that shows the linearity property, right? So we have that this is a linear transformation where v1 was x1, y1, and v2 was x2, y2. So we've shown that T is a linear transformation. We need to show that it's one-to-one and onto. Well, how can we show that this is one-to-one? Well, remember, to show one-to-one, we want to show that T of x equals 0 implies x equals 0, right? If we can show this criteria, then we have a theorem that says this property is true if and only if T is an injection or T is one-to-one. So this is what we need to show. Well, what does it mean that T of x is 0? That means T of xy, which is x plus y, x minus y, is equal to 0, 0, right? Which means we have the following system of equations: x plus y equals 0, x minus y equals 0. Well, the bottom equation tells us that x equals y, and then plugging x equals y into the top equation tells us that 2x equals 0, which means x equals 0, which also means y equals 0. So this system of equations has a unique solution of xy equals 0, 0. And so thus T is one-to-one. Okay, so now we've shown that it's a linear transformation and that it's an injection. Let's show that it's a surjection. What does it mean that it's a surjection? Well, to show that it's a surjection, that means we want to show for every AB in R2, there exists an XY in R2 such that x plus y, x minus y equals AB, right? It means that every element of R2 is hit under this map, basically. If you're thinking about the second R2 as being the target, right? Well, so what that means is, does this system have a solution for all values A and B? Well, to find if it has a solution for all values A and B, we have to set up the augmented matrix corresponding to this system, which would be 1, 1, 1, negative 1, A, B. And for the sake of time, I'll go ahead and just write what I simplified here. And so you get the reduced row echelon form is 1, 0, 0, 1, and then A plus B over 2, and A minus B over 2, which means really that X is A plus B over 2, Y is A minus B over 2, and this is well defined, right? This solution exists for all values A and B here, right? So this implies that T is onto. And so now we've shown that it's a linear transformation, that it's an injection and a surjection, therefore T is an isomorphism. Okay, and so these are the checks you have to go through to prove something is an isomorphism. Okay, let's see here. Next, I think I want to go through a few propositions or important results of a map being an isomorphism. So here's a proposition, and it's if T from V to W is an isomorphism, then T inverse exists. Well, T inverse would be from W to V, right? Then this exists, and T inverse is also an isomorphism. Okay, so basically what we have is, if you have, and you can think about an isomorphism or isomorphic spaces as being just a copy of that space in a different like ambient space, right? In a different dimensional Euclidean space. And so really you can think about, if you have an isomorphism from V to W, right? Well, then you're just kind of finding a copy of V inside, or you're realizing W as a copy of V. Well, certainly you could do the opposite, right? And so kind of intuitively, at least that's what this is saying. We also have a proposition that if you have two isomorphisms, let's say T from V to W and S from W to Z, if these are isomorphisms, then the composition S compose T, which is from V to Z, is also an isomorphism. And we've proven this already, right? In the last video, we showed that composition of injective maps is injective and the composition of surjective maps is surjective. And so juxtaposing those results proves this proposition right here. And so there's one more proposition I want to state here. And it's, let's look at a linear transformation specifically from Rn to itself. Let's say this is a linear transformation with matrix A, i.e. T of X is equal to AX, right? Well then, A invertible implies that T is an isomorphism. Okay, and so really what this is with if we have the A is invertible and then T is an isomorphism, what we can think about then is T is a map from V to W with matrix A. Well, then T inverse, this is an isomorphism, right? So iso. Then T inverse from W to V is an iso with matrix A inverse. right? And so if you want to find the matrix of the inverse, well, you just need to find the inverse matrix, right? Okay, I think this is where I will break for the first part. And then for the next part, we'll look at some more properties of isomorphisms. And then we'll spend some time specifically on the kernel and image of linear transformations.